my name is Jonathan Golob. I am an assistant professor in infectious disease at the University of Michigan and a data scientist. Today, I'm going to be showing you a little bit about how we can access data both in wide and long formats, explain what they are, show some advantages, and how we can use them. I'm going to be showing some microbiome data, more specifically 16S rRNA gene amplicon sequencing. It's just a way of picking a gene that's in every microbe, doing a little bit of PCR, and then basically adding up how many reads match up with each of these distinct sequence variants of a gene that's present in every microbe. So in here, in this format, you can kind of see where we're starting with. There's a bunch of columns, each with a different sequence variant, and then each community or specimen gets a row. There's a couple extra columns here, but then everything after that is just a count, how many reads mapped. And you can kind of see we're almost to a true wide format. In true wide formatted data, there's none of these extra columns. Every column just stores the same thing. It's a matrix. So let's tidy this up using a little bit of filtering. So we're going to do that. We're going to rename it, and we're going to use list comprehension in Python to do it. C for C in SD columns, where SD is in C. And you can kind of see exactly what I'm talking about here. There you, excuse me, if you can see exactly what I'm talking about here. Now, all of the columns are one of the sequence variants. It's a true matrix. This is a little bit of labels. There's nearly 50,000 cells in here, and most of them are zeros. Microbiome data, like a lot of data, is really sparse. There are a couple more dense sequence variants up here at the front, but even there's quite a few zeros. And so it's a little bit inefficient to store all the zeros, but that's fine. So let's do something with this data. Let's transform it. And one of the first things we often like to do is to normalize these counts, the total counts. So instead of looking at raw counts, we want to know what percentage of the reads for each community ended up coming from one of these sequence variants. So how do we do that? Well, first thing we need to do is to sum up how many reads total were acquired. We want to sum up each row. And we can use a little nice function here. So what's going here? I'm taking the matrix I just made. I'm using T or transposing it, rotating it 90 degrees, and then summing up, in this case now, each column. And what does it look like? Well, in front of your astonished eyes, here are the total reads for each of these communities. Now we want to divide all of these cells by this. So how do we do that? Well, we take the SD wide and we rotate it again 90 degrees and then divide it by the sum. And here we are as the percentage of reads. Exactly what we wanted, but one problem, now it's rotated. So let's rotate the whole thing again so we get back to the way we kind of wanted it. ST wide relative abundance is equal to this. Voila, this is what we needed. Wasn't too bad. It's actually a really little bit of code to make that happen. You kind of retain two little annoying problems here. Again, most of the cells in this matrix are zeros. It's just math. And then now in wide format, there's really only a way to store one thing in each cell. So if we want relative abundance and counts, we now need to double it up. So it's not a huge deal for this amount of data, but as we get to bigger and bigger data, where instead of hundreds or thousands of columns, we're talking millions or tens of millions or hundreds of millions of columns, say with metagenomic data, when you're looking at microbial genes in a set of communities. It's even sparser and much wider, and this amount of just sheer data to shovel around where most of it is zero can become limiting. All right, well, let's look at how to look at this same data in a slightly different way. This is going to be in long format. So we'll use our pandas data library to load it into long format. Let's see. There we are. So what is long format? Well, in this one, you have the specimen, you have the feature, and then its count. And so this is kind of like Battleship. You get in what was in our wide format, the row, then the column, and then the count. And the key thing is there are no zeros. The zeros are implicit. You only get an entry in this long format if there's some data there. So you go from just shy of 50,000 data points down to only 3,000. So that's quite a bit improvement in efficiency, which isn't necessarily always the best thing to do here. I'm going to rename count to n reads, just to make this a little bit nicer for us to go to. Voila. All right. We want to do the same thing. We want to now get not just the number of reads, but the relative abundance, or the normalize the total number of reads. So in long format, how do we total it up? Well, we can use in Python a group by function. So we group by specimen, and we want to sum it up. So what does that look like? Well, this looks very familiar. It's a little bit very, very familiar to what we did above when we did our normalization of above. You can kind of see the same number of reads. Great. Let's combine these two together. So we take our SVLong that we had before, read. We want to now merge these two together. So how do we redo that? Well, let's go do a little bit of, let's use a different function in pandas, merge. So we take the SVLong, this little long format data. We want to match up where we basically have every row of this specimen has a total reads column with that one. So we take our little code that we made there. I'm going to again rename, just because again, it's not n reads, it's total reads. When we say left, we want to match on specimen. On the right, it's an index. And voila. And then how do we want to do it? We want to have one entry for every one that was on the left table. And so what does that look like? Here we got it. Now there's a little bit of repetition here, but that's okay. We just added another column. And so let's name this total. We'll keep track of it. So how do we make relative abundance? Well, just a little bit of math. And we put that into our, we add a new column with that. There we have it. It's the exact same thing we had before. And in fact, this is kind of nice. We have three, in fact, very different data points, all in the same data structure. We didn't make a new one. We can just kind of build on the one we're building on. We have both the relative abundance, the number of reads, and the total reads, all in one thing here. Quite nice. What if we want to put this back into wide format? Well, we can. We can do something called pivots. What do we want as our index? We want as our index the specimen. What do we want as the columns? We want our columns to be S sequence variants. And what do we want as our values? Well, let's make this the relative abundance. And here you are. But as we talked about, they're mostly zeros and they weren't there before. So we have to tell Python what to do when there's nothing there. We're going to fill it with a 0. And there you have it. You have a beautiful wide format that was made from the long format. And so you can go and do that. And it's kind of a nice way to sort of go around and do that up. You can go back and forth. What if we want to convert the wide format back to long format? Wide format, if you recall, we have our wide table here, and I'm going to put it above. And you want to convert it to long, you can. And so you can use the melt function. We say ignore index equals to false, and then we reset index. And here's what we get. We get our specimen, our variable, and our value. And we can rename each of these to make it match a little bit nicer, but we got into long format from wide. Now, one thing I want to point out to you is it kept all the zeros. And so we can slice them away if we want to get rid of them later on. But let's now do something a little bit different. These sequence variances are very nice, but maybe we want to actually look at taxonomy, give a name. Well, we have a decoration for each of these sequence variances in taxonomy spaces. And so let's load that in using load it in. And this is, again, in long format. And it's quite nice. It has a lot here going on. In fact, each sequence variant has multiple entries depending on what you want. Do you want genus? Do you want family? Do you want species? And then it's got the name, the lineage, the likelihood, and whether or not it's sort of ambiguous. Well, let's say we just want the genus. So we do SV taxon, want rank is equal to genus. Now we've sliced it down and we have 436 rows, which matches up exactly with how many sequence variants there is. There's now only one entry for each sequence variant, and we have what it is. Let's do that merge business again. So PD merge, we have SV long, and now we have our SV taxon. We want to map on sequence variants, and how again is going to be on the left. What does this look like? Voila. So we have our original specimen, sequence variant, total reads, relative abundance, and then we have all the way here, but now it's a little bit too messy. So let's go back here. We had it for all of them. Again, we want only for the genus. SV taxon want length is equal to genus. Let's try it again. Here we are. Now we have a lot more stuff here. And in fact, it's maybe too much, but the nice thing about long format is you can have all these decorations on here and have it kind of all grouped over here. So let's do long with genus. That's what we just made. What if we want to sum up and get the total relative abundance by genus? Well, we're really well prepped to do that. So we want to group by three things. SV long, group by specimen, SV, and I'll show you what this does now. And this is the kind of thing that's really difficult to do in wide format, but super easy to do in long format with these little tricky group bys. And there you have it. For Anerostipes in this community, there are this many reads and this many fractions. And in fact, I don't want the SV in here anymore. I just want the specimen and tax name to properly sum this up. And there you have it. And in fact, you can kind of see we've already simplified things. So we've gone from 3,000 rows only to 2,000 rows as some sequence variants that both map to the same genus get added up and collapsed into one. So I'm going to reset the index again. And because Python has these fancy things that can have multi-layer indexes, and we don't want that. So SP genus. You can see exactly what I'm talking about. And now we can push this back into wide format, because that often is where this was long format. It was really nice to do all of the adding and combining and merging. But at the end of the day, what you really kind of want is to have this all sort of combined together into one nice little thing. And so let's do that. So SP genus, and let's go ahead and let's pivot it again. So what's our index going to be? Our index is going to be specimen. What's our column going to be? Now it's going to be the tax name. And then the value, let's make this a relative abundance table. And then I'm going to go ahead, as we said, we have to have something to do with the zeros, or where the nulls or zeros. And there you have it. Now we've made a table. There's only 83 columns in it because, again, then we've combined together a lot of different sequence variants. But there's still 100 rows because we started with 100 communities, and we have 100 communities. And now we've made a nice table of all of the outputs by genus. And this is nice to go on and do other analysis with. And that is a brief introduction to wide and long data. The brief summary is, I feel like wide data is often a little bit more intuitive for people when they want to look at it and think about data. But long data is very efficient, very, very easy to quickly add on and transform. Very, very useful to do things like these group bys to sum or consolidate data on a higher order feature and then add in information. And then finally, long data is really efficiently packed because things like zeros, particularly with sparse data, are implicit. And there you are. Thank you very much.